Okay, I will be discussing a novel split inductively coupled piezoelectric transducer for flaw detection in pipes. This work was performed mainly by a graduate student in the civil engineering department, Gong, and assisted by my colleague in the civil engineering department, Oppenheim. The motivation for this work comes from the fact that people are doing hydraulic fracturing to get oil and gas, and when doing hydraulic fracturing operations, there's a lot of piping. This is a photograph of hydraulic fracturing, and the piping is assembled and disassembled when moving from one area to another. And some pieces of the pipe look like this. Oh, by the way, the pressures involved are as high as 15,000 pounds per square inch. And yes, I really do mean that third zero there. So a very high pressure. And the material flowing through these pipes is some sort of fluid which contains particulates. Those particulates cause erosion of the inside of the pipes and in particular components. And that erosion can cause eventual failure. So this is something which you want to detect. So we're looking at the possibility of making a permanently mounted ultrasonic transducer which can be used for monitoring critical components. This is an example of a critical component. This is an elbow. There's two connections. There's one over here, and there's a matching connector over here. This is really a very large nut. And you can see upside down the words fail. What you're seeing over here is what the inside of that component looks like, and this shows the streamlines and the paths of some particles that are moving through this elbow, and those particles strike the surface in a number of places, particularly over here. And right underneath this thick area is where there's a substantial amount of erosion observed by looking at this failed component. And that's what we'd like to detect, the erosion which occurs underneath this thick-walled region. The idea will be to mount one inductively coupled transducer, and we want to use that to insonify the entire critical region, this entire annulus over here. We will record the extended response, sometimes called the coda, to the interrogating pulse, and we eventually want to apply advanced signal processing to detect changes. What I will do here is apply naive signal processing. So this shows the concept of the split inductively coupled transducer. This is the medium under investigation. We have two pieces of PZT. One electrode is common, and we drive the top two electrodes from a secondary of a transformer. The primary of the transformer is driven by a pulse generator, and we measure the return pulse using a data acquisition system. In the case that we will show experimentally, the inductive coupling was achieved by using 16 turns of wire for each of those two inductors and ferrite pot cores. It was by no means mechanically or electrically optimized. It's just to try things out. Now, why do we want to use inductive coupling? First of all, it simplifies doing out-of-phase drive of these two transducers. And secondly, it potentially allows us to make a permanently mounted transducer which would be periodically interrogated. We began by doing some simulations, and I will show also some experiments. And both the simulations and experiments are not done on the structure which we're eventually concerned with. They were done on a piece of thick-walled aluminum pipe, which is relatively short. So that models that thick-walled region that we're concerned about. We perform modeling in 2 dimensions using COMSOL 4.3 in the piezo mode. There was a small amount of damping added so that resonances were not exceedingly narrow. What you see here is the geometry we use for simulation and the 2 piezoelectric transducers up at the top. The left-hand side shows that the elements were very small, and the right-hand side shows that we divided this aluminum into two regions, an interior region and an exterior region, which is the outer 1 centimeter. Okay, the simulations were performed first in sinusoidal steady state, and we calculated the stored energy in the entire volume, or the remaining volume, and the stored energy in the outside annulus. What we're trying to do here is determine where most of the acoustic energy ends up. And what you see is there are two frequencies where we get a substantial amount of acoustic energy, and at both of those frequencies, a substantial amount of the acoustic energy is on the outer wall, but there's also some acoustic energy which is on the inside. These two frequencies, 300 kilohertz and about 650 kilohertz, look like they would be good regions to use for measurements. We performed some transient simulations also using 3 cycles of windowed sinusoid. If we do this at 310 kilohertz, which you recall was one of the frequencies where we have substantial amounts of acoustic energy radiated, this is what we see for the Y displacement. That's the displacement in this direction, 200 microseconds after the exciting pulse. You can clearly see that we've got some transverse waves that are excited at a significant angle with respect to the transducers. If you look closely, you can also see ahead of those some longitudinal waves, and you see some surface waves which are launched along the outer perimeter of the annulus. So this shows what happens a little bit later in time. The waves are propagating and reflecting and propagating and reflecting. And even later, we can see the same thing continuing. The surface waves along the outer perimeter continue to exist for a considerable time. We have performed experiments using the same inner and outer diameters, a segment of aluminum pipe which was 8 centimeters long. You can see the mounted piezo transducers over here, and the inductive coupling is outside of the picture. This photograph shows an eroded region on the inside which was created using a Dremel type tool. So first, without creating a defect, we recorded transients at 9 different center frequencies between 100 kilohertz and 1,000 kilohertz. There's substantial ultrasonic energy out to 1,000 microseconds, which corresponds to many traversals around the perimeter of the pipe. In fact, at some frequencies, for example, 100 kilohertz and this frequency over here, you see some regularly spaced arrivals. Those arrivals are reasonably consistent with a complete path around the pipe at the transverse velocity in aluminum. Now, we evaluated the total signal energy in that transient by integrating the square of the voltage over time between 100 microseconds and 1,000 microseconds by starting our integration at 100 microseconds. We avoid this region, this area over here where the exciting pulse gives us a substantial amount of signal. So we're integrating only for 100 microseconds to 1,000 microseconds. So that's all returned energy. We see that there's a peak in that returned energy near 300 kilohertz and also near 650 kilohertz, in very good agreement with what we saw for the simulations. We have performed a flaw detection study on 2 separate specimens. We simulated flaws by performing erosions or creating erosions on the outer perimeter and on a separate specimen on the inner perimeter. Those flaws were created at about 120 degrees around the specimen. In other words, not exactly opposite the transducer, not at 90 degrees. We had two separate steps of mass loss, 1/10 of a gram and 1/2 a gram. We measured, before creating the defect, a reference transient, and we measured transients with damage at the two different damage steps. We computed the difference between the transient measured with damage and the reference signal, and we evaluated the difference signal energy between 100 microseconds and 1,000 microseconds. So that is naive signal processing. Indeed, even looking at the raw transient, this is at 650 kilohertz, you can see some discernible signal differences between the three signals for the reference, 0.1 gram mass loss and 0.5 gram mass loss. The blue signal and the green signal are visible separate from the red signal, which was the reference. I'm sorry, the blue signal, which was the reference. So there's visible changes even in the raw data. This is for the flaw on the outside of the pipe. So performing that study for several frequencies between 100 and 1,000 kilohertz and computing the difference signal energy, we see a plot like this. We see a substantial change when we increase the mass loss at the 300 kilohertz range and the 600 kilohertz range. And if we do the same thing for a flaw on the inside, we also see discernible changes in that integrated energy, although they're a little bit smaller. And if we compare inside versus outside, flaws on the outer surface give a larger fractional change than flaws on the inner surface, but both types of flaws are readily detectable using this relatively naive way of analyzing the data. So, conclusion. A split transducer does allow us to effectively insonify the entire volume. Small amounts of erosion are readily detectable. There's a somewhat larger signal for the outer surface erosion, which is not what we're most concerned with, and that's consistent with the simulations. This work was supported by the Pennsylvania